So now we're going to finish problem number 2 from the 2018 AP Chemistry free response. We're going to look at D through F. So just jumping right into it. N2O3 reacts with water to form nitrous acid, a compound involved in the production of acid rain. Sometimes you'll hear the little saying that SOx and NOx compounds are involved in the production of acid rain, and that is definitely a NOx compound, a nitrogen-oxygen compound. So the skeletal structure of HNO2 is shown below, and we are asked to complete its Lewis structure, including any lone pairs, and then identify the hybridization of the nitrogen. So looking at this, we have HO and O, so we'll just be very careful here. 1 valence electron, plus 5 is 6, plus 6 is 12, plus 6, we're looking at 18 valence electrons available. We always start with single bonds, so 2, 4, 6, we're down to 12. Make the outside or terminal atoms happy first. So when we do that, the hydrogen is already happy, so to speak. It has 2 electrons, which hydrogen is just fine with. That oxygen only has 2, so we give it 6 more. 6 remain. And I'm going to choose to make the oxygen have an octet, and that leaves 2 for the nitrogen. So that is 18 electrons, but the nitrogen does not have an octet when we check to make sure that everybody's happy. And when we look at CNOPs, which isn't perfect, there are other elements that can double or triple bond, but CNOPs, these are the 5 elements that most commonly double or triple bond with each other. It's just a good rule of thumb to go with. Nitrogen and oxygen both are, because this one has so many lone pairs, I'm going to choose to take 1 from it, and I'm going to make a double bond. That oxygen still has an octet, and now that nitrogen does. And that would be an acceptable Lewis structure for HONO, and it would be worth 1 point. For the hybridization, we just have to be careful and think back. Hybridization is based on the number of electron sites around the element in question, and a single bond, a double bond, a lone pair, a triple bond, they all count as 1 site each. So 1, 2, 3. And so remember, the first site you count represents S, and the next 3 would count for P. Now AP Chemistry does not go past that, so sp3 is the greatest hybridization that you would see, but this would be sp2. First one we count as an S, and then the other 2, they are P. So sp2 hybridization, and that is worth 1 point. So now, to look at the rest of this problem, we have a paragraph here saying we want to determine the concentration of HNO2. To do that, we titrate 100 milliliters of it with a 0.1 molar potassium hydroxide solution, and we are given the titration curve showing the change in pH as KOH is added. Here's our net ionic equation. So we can tell right off the bat, we've looked at a lot of graphs like this, that this is definitely a weak acid. HNO2 is a weak acid. It's not one of our strong that we're supposed to memorize. We know because the initial pH is around 2.5. We usually expect strong acids to have a pH lower of around 1 or so. Note that here we have this little, gradual increase, and then all of a sudden we have this decrease, but this has the look of what we call the land of buffer, where during the titration, as the OH minus is the limiting reactant, well, it's gone, there is excess weak acid, and its conjugate base has been made, so we have a buffer during this region. So to answer the questions involved, determine the initial concentration of HNO2. Well, we know that when the pH skyrockets, the middle part of the vertical region is the equivalence point, where the number of moles of our two reactants are present in enough quantities so that they cancel each other out. So that is 20 milliliters, and it was 0.1 molar KOH. So we could solve for the moles of the OH minus and use that to help get the molarity of HNO2, which is what we've been asked to solve for. So we know that it's 20 milliliters, so 0.02, let me double check, just 0.020 liters, and we'll multiply by 0.1 molar. And so that gets us 0.002 molar for an answer. Moles of OH minus. Well, this is really nice. It's a 1-to-1 ratio. So this many moles of hydroxide, due to the 1-to-1 ratio, it's the exact same number of moles of HNO2 must have been present to react with. And now for the molarity, we recall that it was 100 milliliters, so 0.1 liters. So we would get an answer of 0.02 molar for the concentration of our HNO2. And that whole thing was actually just a 1-point problem right there. You might guess that maybe there's another point in there somewhere, but that is actually just worth 1 point. So now we go back to the problem, and we are asked to determine the value of the pKa. So you might remember, so we're asked for the pKa. Well, P means negative log of. We want the negative log of the Ka for this acid, weak acid. Well, here's the equivalence point at 20. Well, if we go back to 10, this is the halfway to the equivalence point, which is a really nice, important thing to look at. Due to our buffer equation, we know that, and this is the buffer equation that we use, that the hydrogen ion value is equal to the Ka times the moles of the acid over the moles of the base. Well, halfway to the equivalence point, the acid-base ratio of the buffer is equal to 1. So the Ka is equal to the H+, which means the pH is equal to the pKa. So all we have to really do here is read our little chart, and we see when we do that since at 10 milliliters is a halfway to the equivalence point, we come over to a little above 3. On the answer key, it says the correct answer is 3.4. Any answer around 3.4 for the pKa got a point for E Part 2. So now to finish, during the titration, after a volume of 15 milliliters, a 0.1 molar KOH has been added. Which species, the weak acid or its conjugate base, is present at a higher concentration? Well, we just talked about 10 milliliters is halfway to the equivalence point, and that is when the weak acid and its conjugate base have a 1-to-1 ratio. They're present in equal amounts. So before that, as we discussed in class, the acid part in this scenario, which would be HNO2, is present in greater amount than the conjugate base. But after that, we have more conjugate base. Remember, HNO2, as this titration is happening, is decreasing and decreasing and decreasing, while NO2 minus is steadily increasing. It just so happens at 10 milliliters, they have reached the same value. Well, this is at 15 milliliters, so that means the product, in this case, the conjugate base NO2 minus, is present in a greater amount than the reactant HNO2. We are supposed to justify our answer. So our answer is NO2 minus is present at a higher concentration because at 15 milliliters, we are past halfway to the equivalence point, so we will have more product conjugate base than reactant HNO2 left over. And that was worth 1 point as well to finish out this problem. So again, D up at the top, that was 1.4.020 molar HNO2. The pKa is 3.4. That was worth 1 point. It's 1 point for stating that NO2 minus is present, and you relate to the conjugate base is present more than the acid. And then up at the very top, it was 2 points, 1 point for the Lewis structure and 1 point for sp2. And that finishes problem number 2 from the 2018 AP Chemistry Free Response.